Hello everyone. In this lecture, we will not introduce any new cryptography topics. Instead, we will focus on the topic of data encoding. We will learn how to encode different data types using distinguished encoding rules defined by Abstract Syntax Notation 1 or ASN1. So what is ASN1? As the definition says, ASN1 is a standard interface description language for defining data structures that can be serialized and deserialized in a cross-platform way. It is broadly used in telecommunications and computer networking, and especially in cryptography. And indeed, the reason why we have to deal with ASN1 in this course is because most standards in cryptography use ASN1 to describe data protocols, formats for keys, certificates, and to describe many other related data structures. And this concerns not only applied cryptography. If you plan to do anything engineering related in computer science, it will be very hard for you to avoid ASN1. And this is the reason why in this course we are spending an entire lecture on this topic. Those of you who have a telecommunications background should already be familiar with ASN1, but we will start here from zero. So let's start. To begin with, ASN1 is a notation to describe abstract data types and values. ASN1 notation describes information, not its representation. As we will see in a minute, there are ASN1 standards that deal with data representation, but the ASN1 notation itself deals only with abstract definition of data structures. For example, if you are to develop a new communications protocol, you can use ASN1 to describe the protocol on quite a detailed level without having to deal with the question of how the data will be encoded for transmission. Then you will give your protocol description to engineers, and they, based on practical considerations, will then decide what encoding mechanism to use for encoding the data. So the idea of ASN1 is that it is similar to the XML schema. However, ASN1 is rich with built-in data types. And ASN1 on its own is not tied to any particular encoding mechanism. Yes, we can encode ASN1 data to XML as well, but not necessarily, as you will see. Let's look at an example. So here is some simple data structure described using ASN1 notation. It defines data structure for two messages, my question and my answer, and these two structures have been bundled together in the so-called ASN1 module named myQA protocol. What we see here is that my question is a sequence with two fields, ID and text. ID is an integer in the range from 0 to 999, and the text is some UTF encoded string. And then we have the data structure my answer, which has the same fields, the field ID, which most likely contains the ID of the asked question here, and the text field, which contains the answer to the question asked here. A very simple example, but I think it gives you an idea of how to use ASN1 to describe fields of a protocol. As I said, ASN1 provides a list of several simple built-in data types. Therefore, let's go through the most popular ones. So there is the ASN1 null data type to encode a null value, which maybe does not seem to be a particularly useful data type. Boolean to encode true or false. Integer to encode whole numbers from -infinity to +infinity. So as you see here, since we are dealing with abstract data types, at this point we really don't care about practical length limitations that we will face when we will have to encode this data for storage or transmission. Real data type to encode floating point numbers using mantissa base exponent representation. Octet string to encode arbitrary byte strings. Bitstring data type if you want to encode bit values, zeros and ones. This is useful if our bit strings are not full bytes, and hence we cannot use the octet string data type. UTF-8 string to store UTF-8 encoded Unicode characters. Numeric string for space and digits. Printable string for printable ASCII characters. AI5 string for ASCII characters in this specific range. And finally, UTC time to encode time in the form year, month, day, hours, minutes, seconds, and the time zone offset here. There are more data types, but these are the most popular which we will see in this course. Then there are also a few built-in structured data types, which can be used to construct more complex data structures. For example, sequence data type that can contain several other values of different data types, as we see here. Then there is data type set. The set is very similar to sequence. The only difference is that sequence is ordered, while set can have these values encoded in any order. Another structured data type is choice. In choice, as the name indicates, only one of these defined values must be present. Okay. Note that the values can be nested. For example, sequence can contain another sequence inside it, which in turn contains yet another sequence, and so on. I hope it makes sense. Then next, a somewhat more complex data type is object identifier. As its name implies, we can use it to uniquely identify objects. The object here can be anything, but usually object identifiers are used to identify a document with a specific version, cryptographic standards, algorithms, and so on. Most of the time, we will see object identifiers being used to reference specific cryptographic algorithms. For example, here you see the object identifier of the RSA encryption algorithm. As you see, the object identifier is a list of numbers joined together using a dot. And each number here actually represents a node in the object identifier tree. Here is how the tree looks. So for convenience, each node in the tree is assigned a name. We can take the object identifier of RSA algorithm and see what each number represents here. You can use this website to browse the object identifier tree, and there you can also register your own branch in this tree, which then will not be allocated to anyone else. This way, if you invent a new crypto system or protocol, you can assign a unique object identifier for it. Very good. So now we know how ASN.1 notation looks, but at the end of the day, we will have to implement this protocol in practice, and this is when we have to answer the question of how to encode this data structure for transmission. So how do we encode or serialize this structure for transmission? How to convert this data to bits and bytes? As I mentioned before, even though ASN.1 on its own is an abstract syntax notation which does not deal with encoding, the ASN.1 standard provides several encoding rules for encoding the data defined by ASN.1 notation. Let's have a look at the list of standard ASN.1 encoding rules. The first, bare or basic encoding rules, is a binary encoding mechanism which encodes ASN.1 data by encoding their type, length, and value. Then there, or distinguished encoding rules, is a subset of bare encoding, with the only difference being that there is more restrictive. While bare provides some flexibility on how to encode the data, in there, the same data value can be encoded in only one valid way. This is the reason why there is preferred to encode cryptographic values, because then we can simply easily bit-to-bit compare to check whether two there encoded structures contain encoding of the same data. Pair or packed encoding rules is a very space-efficient encoding mechanism useful when we have to save bandwidth, but that mechanism also introduces more complexity. XER or XML encoding rules allow us to encode data using XML. And the recent standards also propose JSON encoding rules to encode ASN.1 data. Let's take a quick look at the example of XML encoding rules. So here is our ASN.1 notation. And this is how it will look when XER encoded. So what can we observe here? First, that it is human readable. The tag names preserve the names of ASN fields. You see the tag name question text here maps to the question text field here in the ASN.1 notation. However, the information about the type is lost. By looking at this encoded structure, we don't know what ASN.1 data type this value has. This is 42, but is it an integer or string? Usually this is not important because we assume that the sender and recipient both share the ASN1 protocol description. So it does not matter that here we have no type because we can recover it using this ASN1 data description. The problem is that XML is not a very efficient encoding. We are spending quite a few bytes to transmit tag values. The longer our ASN1 field names are, the more space the encoded structure will consume, which maybe is not that good. Another problem with XER is that if you want to compare XML data structures, we need to apply the process called canonicalization. Because in XML, there is no semantic difference in how many space characters, for example, we use here for indentation. However, if we try to compare bit by bit two encoded values, the result will be different if different spacing is used, and so on. So canonicalization is a type of normalization which will transform XML encoded data using common agreed upon normalization rules. This canonicalization actually is not that trivial in practice, and therefore this is something we would like to avoid. All right. So in this course, we will only focus on the DER or distinguished encoding rules. The DER encoding is not human readable. However, it has quite an efficient encoding. As I said, a value can be encoded only in a single way, and the data is encoded as a so-called type length value or TLV element, and here's what it means. Let's say that we have a field message which is of ASN1 type UTF-8 string, and it contains the value hello, as you see here. So how do we encode it using ASN1 DER encoding? What we have to do is to build a type length value TLV element by encoding type, length, and value. So the type here is UTF-8 string. The length here is 5 bytes because hello in UTF-8 encoding consumes 5 bytes. And the value is hello. So if we DER encode all of this, we will have a DER encoded value consisting of these 7 bytes. This byte encodes type, this byte encodes the length, and these are the value bytes H, E, L, L, O. And we can verify it. We can write these 7 bytes in a file using the echo command. Then we can install this nice tool called dump-ASN1, which is able to parse DER encoded data. We run this tool specifying the file as an argument, and it shows us that it contains UTF-8 string encoded value hello. What we see in the output is that DER encoding does not retain the name of the field of the ASN1 notation, so the name message is not present here. However, compared to XML encoding, DER encoding preserves the type of the value, as you see UTF-8 string here. Note that if we use some structured data type, then the value bytes here would be DER encoded data, which may contain more DER encoded data inside, and so on and so on. So that's how DER encoding works. If you got the idea, we can now move forward. So let's move directly to the homework. The homework here is to implement an ASN1 DER encoder. This is probably one of the hardest homework tasks in this course, but the homework is quite rewarding, so to say, because you will understand how to encode different data types to bits and bytes, and will learn how to do it efficiently using bitwise operations. So what you have to do here is to implement an ASN1 DER encoder that can encode a subset of ASN1 data types by implementing the following functions. The idea is that your solution will implement these Python methods, which can be called by passing the value as an argument. For example, in case of ASN1 boolean, the argument can be Python's boolean type containing true or false, and this method then has to return a bytes object which contains their encoding of that boolean value. The same for integer, bit string, and so on. In the following homework tasks, we will use this encoder to encode the data structures that we will work with in this course. Therefore, it is crucial for you to complete this homework. In addition, as a type of test case, your solution has to encode this artificial ASN1 data structure. So your solution must produce a dir-encoded file, which if dumped using dump ASN1 tool, should produce the output as shown here, and the output must match bit by bit. So how will you create this structure? You will construct it by calling your encoding functions in the correct order and passing the correct arguments to them. So you have ASN1 boolean true here, which corresponds to this boolean true position here. Then ASN1 set here, which corresponds to this set here, and so on. So you have to complete the missing parts here. Okay? Your ASN1 encoder will accept an argument from the command line where this ASN1 dir-encoded data structure should be written. In this example, the file name passed to the ASN1 encoder here is asn1.dir. Now, over the next few slides, I will explain how these dir type, length, and value bytes are constructed for each of the data types your encoder must support. Let's start with the type byte. So what does it encode? Here you can see what each bit in the type byte designates. So the first two bits, leftmost bits, encode the class. 00 universal, 01 application, 10 context defined, 11 private. The standard ASN1 data types will use the universal class, so zeros here. Then there exist application specific and context defined classes, whatever they are. If you want to invent your own data type, you should denote it by using this private class here. The fifth bit specifies form, either primitive or constructed. Most of the standard data types are primitive. The constructed data types are those which can contain other data types inside. For example, sequence, set, and choice. The 5 rightmost bits encode the data type used. Here you can see the corresponding 5-bit values for the standard data types. Now, we can use this data to dissect this type byte from the example on previous slides. Let's say we have this type byte here with this hex value, which maps to this bit string. We see that these two bits are 00, which maps to universal. This bit is 0, which means primitive data type, and these 5 bits correspond to data type UTF-8 string, because we have 01100 here and 01100 here. Okay? If you want to learn more on ASN1 and dir, here are some links for you, but in general, that's not needed, as I will try to cover all the needed information on the slides. All right, so it is clear about the type byte. What about the length byte? How is the length encoded? For the homework, we will create the ASN1 len helper function. This is useful because the length encoding for all data types is the same. Therefore, we can implement the length encoding logic here, and then we can simply call this function from the methods that will implement encoding of the specific data type. So, as an argument, this function will get the value bytes of the TLV element, and based on the size of this value, this method will return the length bytes of the TLV element. Now, how do we encode the length? If the value is small, we can use just 1 byte to encode the length, but if the value is bigger, we will need several bytes to represent the length of the value. And here is how it works. If the number of value bytes are less than 128, then the length byte encodes the number of bytes in the value. So if this variable value bytes has 5 bytes in it, then your ASN1 len method will return a bytes object containing a single byte with the value 5. But if the size of this byte string is 128 bytes and more, you have to use more advanced encoding. In that case, the most significant bit of the first length byte is set to 1, and the remaining 7 bits encode the number of length bytes that follow. And then the following length bytes encode the number of value bytes. The suggestion is to use the IB function from the first homework without the length parameter. Okay, Maybe it sounds a bit complicated, but let's take an example. So, to encode length for a value which is 126 bytes long, we simply return a single byte with the value 126 as the length byte. The same applies for the length of 127. However, with the length 128, we have to use 2 bytes. In the first byte, we set the most significant bit to 1, and in the remaining bits, we specify how many length bytes will follow. In this case, it is 1, because to encode number 128, we need just 1 byte. And this byte is the encoding of number 128. To encode the length 1027, we need 2 bytes. These 2 bytes are the encoding of 1027. The first byte of the length byte will have this bit set, and the remaining 7 bits specify number 2 because 1027 is encoded using 2 bytes, and so on. If the encoding of the length of the value requires 3 bytes, then encode it to 3 bytes and prepend a byte where these 7 bits specify number 3 and the most significant bit is set. Okay? Okay. In theory, we could always use this long form where the first byte specifies how many length bytes follow, but then we would waste an extra byte if the length can be encoded in a single byte. The DER encoding standard requires using the shortest possible form to encode the length. Now let's go through the encoding of the values of different ASN1 data types. Let's start with ASN1 Boolean. ASN1 Boolean encodes a Boolean value. The type byte will be 00000001, which corresponds to universal primitive tag 1, because tag 1 corresponds to ASN1 Boolean data type, as you saw a few slides back. The value byte contains 0 byte for false and byte with value 255 to denote true. The encoding of Boolean has already been implemented for you in the homework template. ASN1 integer encodes an integer value. It can also encode negative integers, but for our needs, we must only support encoding of positive integers. So the type byte will correspond to universal primitive tag 2. So the only change from this type byte here is in the tag value. Instead of 1 here, you will have 10 encoding number 2. Okay? The integer itself is encoded using 2's complement integer encoding, which basically means that the most significant bit encodes the sign, indicates whether the value is negative or positive. What you should do is first convert the integer to byte string using the IB method without the length parameter. Then, in case the most significant bit of the most significant byte for a positive integer is 1, then prepend a 0 byte, because otherwise it will be recognized as a negative integer, which we don't want. Note that the integer value 0 is encoded as 0 byte instead of an empty value. This is a corner case which you must be aware of. Let's look at an example. Let's say we want to encode integer 140. This last byte is 140, but since the most significant bit here is 1, we have added this padding 0 byte to make sure that the most significant bit now is 0, and therefore the value will be recognized as a positive integer. The length byte is 2 because the integer is encoded using these 2 bytes. And the type byte represents ASN1 integer encoded value universal primitive tag 2. If we had a case where there was some other value where the most significant bit was not 1, then we would not need this extra padding byte here. Okay? I hope it's clear about ASN1 integer encoding. A quick side note. Some years ago, there was an interesting case with the Estonian ID card, where it turned out that the public key certificates in the ID card were encoded ignoring the requirement to add this padding byte here. As a result, more than 250,000 ID cards were found to contain incorrectly encoded certificates. Here is an excerpt from the news article. A coding mistake made by the certification center, the company behind the software of ID cards, means 250,000 ID cards could cause problems for users in the future. The problem concerns Estonian ID cards issued between September 2014 and September 2015, and if not fixed, will mean users will be unable to use ID cards with the new version of the Google Chrome browser. We let a fault slip through our software development process, told the head of the company. And the problem surfaced when Google worked out a new version of Chrome, which has more detailed checks. So actually, the problem was there for years, but it was not detected because the most popular cryptographic libraries, such as OpenSSL, even today treat integers as positive, even if they do not have the padding byte in their encoding. However, when Google made their Chrome browser, they wrote their own cryptographic library that very strictly enforced the standard. And hence, the certificates of the Estonian ID card were suddenly recognized as containing negative integers and therefore were rejected by the library. To solve this problem with these cards, the Estonian government implemented a solution such that cardholders could replace the incorrectly encoded certificates on their ID cards. So this is a nice real-world example of what happens when standards are not fully followed. So don't make this mistake. Don't forget about the padding byte. All right, ASN.1 bitstring. ASN.1 bitstring encodes an arbitrary bitstring value. Universal primitive tag 3. The bitstring data type is useful as it allows us to encode bitstrings whose length is not a multiple of 8, meaning that they do not consume full bytes. However, to encode such a bitstring, we still need to pad our incomplete bitstring to form a full byte, since for any type of storage, we have to use full bytes. For example, we cannot write just a few bits into a file, right? So bitstring is write padded with 0 bits to form a full byte string. Since we have to somehow communicate to the recipient how many padding bits we added, the first byte of the value bytes will encode the number of padding bits appended. Here is an example to encode 6-bit bitstring 010101. So here we have write padded it with 2 zeros and prepended a byte which encodes the number of padding bits. So this byte encodes number 2 because we added 2 extra bits here. The length byte is 2 because our bitstring is encoded using these 2 bytes here. And the type byte corresponds to a ASN.1 bitstring type. If we were to encode a bitstring which is multiple of 8, we would have zeros in this padding byte. In their encoding, the padding value here can be only in the range from 0 to 7. Therefore, to encode an empty bitstring, the value would just be a single padding byte specifying padding with value 0. Okay? ASN.1 octet string encodes arbitrary string of octets or bytes. So this is super trivial to implement. We just take whatever is passed as the argument, put it into the value bytes, prepend length bytes, and encode the type byte using universal primitive tag 4. Okay? ASN.1 null encodes a null value. The type byte corresponds to universal primitive tag 5. It has no value bytes, therefore the length byte will be always 0. Object identifier is the most complicated type to encode. It encodes an object identifier, which is a sequence of integer components. The type byte encodes universal primitive tag 6. Your ASN.1 object identifier method will receive a list of integers object identifier components. Now the question is how to encode these object identifier components to dir. The first value byte will be the constant 40 multiplied by component 1 plus component 2. The possible range for the first 2 components is limited, therefore it is guaranteed that this value will not exceed the value that can be encoded in 1 byte. The following value bytes encode the remaining object identifier components. However, each component is only encoded using the 7 rightmost bits of the encoded byte, because the 8th bit of the most significant bit is used as a flag to indicate the last byte of the encoded component. Therefore, each encoded byte's leftmost bit, except for the last one, is set to 1. Let's look at an example. Let's say you want to encode the subject identifier with components 1, 2, and 840. This is how the DER encoding will look. The type byte encodes universal primitive tag 6. The length byte encodes number 3 because we need 3 bytes to encode the subject identifier. The first 2 components go into this byte. The last component, 840, is encoded using 2 bytes here. As you see, only the 7 rightmost bits are used to encode the value 840. The most significant bits are reserved to mark the last byte of the encoded component. This bit is 1, which means that this is not the last byte of the component, while this bit here is 0, signaling that this is the last byte for the component. So if a component needs to be encoded using several bytes, only for the last byte this bit will be 0. For all the preceding bytes of the component, this bit will be 1. I hope it is clear. Here you can use a modified IB function from the first homework, but which works on 7 bits. Masks out 7 bits, setting the 8th bit to 1, and so on. Okay? Okay. Now, to the encoding of sequence is quite straightforward, except that please note that the type byte has the constructed type. Therefore, the corresponding bit in the type byte must be set to 1. The value bytes contain their encoded data. You don't have to validate it. Simply put whatever is passed here as the argument into the value bytes. Okay. ASN1 set is the same, just that the value of the tag bits encode the number 17. The value bytes contain their encoded data. ASN1 UTF-8 string encodes UTF-8 encoded Unicode characters, universal primitive tag 12. The value bytes contain UTF-8 encoded characters, so simply put the bytes passed as an argument into the value bytes. ASN1 UTC time encodes coordinated universal time, universal primitive tag 23. The value bytes contain string representation of the time in this form. So year is encoded using 2 ASCII digits, the same for month, day, hours, minutes, and seconds. The capital Z character must be here indicating no time zone offset from UTC, because in their encoding, the time zone offset must not be used in UTC time encoding. Okay? As you see, the time is encoded using string representation, which is not a very compact encoding. It is likely that the encoding is kept this way to not make the encoding too complicated. Now, due to this string encoding, it is actually quite easy to spot their encoded data. For example, if you open some their encoded binary file in text editor, you will be able to immediately spot this time encoding, and then you can suspect that the file may contain their encoded data. The last ASN1 topic for this lecture is tagging, and here is why it is used. In some cases, ASN1 notation may be ambiguous. Here is an example of such an ambiguous ASN1 structure. So here we have some sequence which can contain 2 integer values, value 1 and value 2, and both of them are optional. What it means is that we will be unable to decode the structure if the encoded structure contains only one value, right? Because the decoder will not be able to figure out which of the optional values is present, value 1 or value 2. One way to fix this is to tag the values. So we would assign tag 1 to this optional integer value and tag 2 to this value. Problem solved. Notice that there are 2 methods available to tag a value, using either implicit or explicit tagging. The difference is that implicit tagging overrides the existing TLV type byte or the TLV value to be tagged. So we are losing the original type value. This basically means that it is problematic to decode data structures which have implicit tags unless we give the decoder the ASN1 description of the data structure. A nicer approach is used by explicit tagging. The explicit tagging prepends type and length bytes, effectively encapsulating the original TLV into the value bytes. In your ASN1 encoder, you have to implement explicit tagging. Just a note that if the ASN1 notation does not have this keyword specifying the tagging method, then the explicit method must be used to tag the value. So you will have the method ASN1 tag explicit, which expects two arguments. The first argument is the encoded data to tag, and the second argument is the number of the tag. So what it does is it tags, encapsulates any data type. The type byte is context-defined, constructed, and the tag value is encoded in the 5 rightmost bits. Now, as you see, the tag value, which can be encoded using just 5 bits, is limited. It is actually possible to encode larger tag values using multiple bytes, but for our purposes, we do not need to support tags larger than 30. The value bytes will contain the encoded data that we want to tag. Here is an example. Let's say we have a sequence which contains a null value and we want to tag it using the tag number 5. So this is how we will call our encoder functions, and as a result, this variable ASN1 will contain the encoded tag data. This value we can then write in a file named asn1.dir and dump asn1 it. And this is what we will see. Sequence containing null tagged with tag value 5. Okay? All right. Very good. We are done with ASN1 except for the last note. Banned functions for this homework. Your solution must not use functions bin, hex, stir, int, byte array, divmod, exponentiation operations, and division and modulus, unless needed for legitimate purpose, for example, for computing bitstring padding size. Use bitwise operations as much as possible. If you are implementing the functionality using any of these functions, you are doing something very wrong. As an example, for instance, to convert a string containing bit representation to integer, you can use the following loop. For bit in this string, left shift I by 1. If this bit character contains ASCII representation of digit 1, bitwise or variable I with 1, otherwise do nothing, it will stay 0. So as a result of this loop, the variable I will contain integer representation of this bit string. Makes sense? I hope it does. As a general rule, for all future homework tasks as well, encoding values to bin and hex representation is only allowed for printing out non-printable binary data. That's it. If you are using bin and hex functions to do some binary data decoding, you are doing something very inefficient and wrong for our purpose. Okay, good. We are done with this lecture. Good luck with your homework.